Okay, I think it's about time we get started here a couple minutes after the hour. I'm guessing a couple more people will join in, but I think we can't wait for everybody. So I guess I will just introduce Leah Shandross, who's going to talk to us about hospitalization forecasting. So Leah, the floor is yours.
All right, thank you very much. Hello, everyone. I'm Lee Shandross from Reich Lab at UMass Amherst, and today I'm going to be talking about my work with forecasting COVID-19 incident hospitalizations with temporal hierarchies. So first, I want to begin with a little bit of motivation. So I'm sure that all of you have heard at least something about COVID-19 forecasting, and you might have seen that there's definitely some sort of inconsistent model performance among current forecasting models. And this is a result of the non-stationarity from policy changes, behavioral shifts, and variance, as well as the forecasting feedback loop, which basically describes the fact that our forecasts are having an impact on the system being forecast. So we see some especially bad performance when trends are changing. Particularly, many models aren't even assigning probability to these types of large changes. And so you can see in the figure here below, I've circled in red a couple of instances where a model is predicting that the trend isn't going to change when in fact it did change. So if the model performance is not always so good, why is forecasting even important then? Well, local, state, and federal organizations use forecasts for public health planning for things like resource allocation, policymaking, and risk communication. Additionally, businesses and other organizations must account for the economic impact of disease outbreaks. So we'll see things like loss of productivity or worker hours, as well as potential financial loss in industries with perceived connection to the disease at hand. An additional point that I would like to make is that even endemic diseases impact hospital usage and are therefore monitored and forecast. And so that brings us to introducing one type of approach that we can use for forecasting, temporal hierarchical forecasting, which abbreviates to THIEF. This is a novel method developed by Athanasopoulos in 2017 that combines hierarchical forecasting and temporal aggregation for time series. So this approach consists of three main steps. First, to create the temporal hierarchy. The second is to generate base forecasts for every level of the hierarchy. And third, to reconcile those forecasts. So reconciliation describes the process of making hierarchical forecasts coherent. Well, what is coherency? Coherency is a property of hierarchical forecasts that basically means forecasts at lower levels add up to the forecasts at higher levels. So this only becomes an issue when forecasts don't agree and we don't know which level of them to trust. So in terms of THIEF, it basically makes forecasts at every level and then combines them with weights determined by each level's expected accuracy. And so as a result, we get the benefit of forecast combination as well as coherence. So there are many forecasting methods that we could choose to use. So why use THIEF over them? First, THIEF uses an underlying classic statistical model, and research has indicated that these models show good performance for infectious disease forecasting. Second, THIEF has demonstrated significant performance gains in other settings like operations management, and we're hoping such accuracy improvements may translate over. Third, to my knowledge, this is an untested methodology within the infectious disease context, and so we're hoping that it could offer some new insights into COVID-19 forecasting. Specifically, we're hoping that the aggregation levels of the hierarchy may be useful to providing those new insights. And so we're including both shorter aggregations in order to help cancel out noise from reporting artifacts, since I'm sure that you all know that surveillance data can often be quite noisy, while longer aggregation levels are also included in order to investigate the potential existence of longer term trends. And if they do exist, hopefully that would help us make better forecasts. So the overall objective for this work is to determine if THIEF can produce a probabilistic forecasting model for COVID-19 instant hospitalizations in the US that is consistently better than a naive baseline model. And just as a quick point of reference, usually around half or a little more of existing models beat the baseline depending on how far out we are forecasting. So just a little bit about the data. We use Health Data's COVID-19 instant hospitalization truth data on which to train our models. Something else about this data is that it's not static. And by that, I mean that corrections and adjustments are being made to better reflect what we suspect to be the true instant hospitalizations. And so this basically means that some values within the data set might change from week to week, especially the most recent entries. Those probably are not necessarily going to be finalized and like sort of reflect those best guess values. So that means that we have a choice when building our model about using the fully revised data versus available as of the forecasting date data. So for the unversioned data, that's going to be cleaner and a bit simpler to implement. But on the other hand, the version data, which updates from week to week with any of these adjustments, is going to be more reflective of the actual data that current hospitalization forecasting models are using. And so that would allow us to have a sort of fair comparison against other models. And so because of that, we choose to use the version data. So a couple of other things about the methods. These forecasts that we're making are probabilistic, and so we are using quantiles to define the full probability distribution. The 23 here are specified by the COVID-19 Forecast Hub, which is why we use them. And for this work, we are obtaining these quantiles from prediction interval bounds because THEIF as an approach is actually only defined for point forecasting. So we need to use prediction intervals instead of in order to generate the full distribution. So for example, the 90% prediction interval consists of the 5th quantile and the 95th quantile. We choose to forecast for 53 total locations, which include the 50 states, Washington, D.C., Puerto Rico, as well as the U.S. as a whole. And we leave out any other extremely low count jurisdictions because they're not going to be providing any meaningful contributions to this analysis. So we are performing a retrospective analysis on the period of July 27th, 2020 until November 1st, 2021, with a training and test phase split on July 5th, 2021. And this split is done in order to have each of the phases, including full pandemic waves. So a couple of other things about the period of analysis. You may notice that it starts maybe a little later in 2020 than one would expect. This is because we only see hospitalization data becoming consistent for all and reliable for all 53 locations of interest on July 27th. Meanwhile, forecasts are made starting December 7th, 2020, because that is when the health data source was declared the official ground truth data. One last thing is that in this presentation, we are actually only showing training phase results because we are trying to be careful about not looking ahead to the testing phase data prematurely. A little bit more on methods. We choose to make 6 total methods through the THEIF approach, the combination of 3 hierarchy schemes and 2 data transforms, but all of them use the ARIMA base forecaster. The 3 hierarchy schemes are detailed here in the figure on the right, with topmost 4-week, 8-week, and 12-week levels. Something to know is that all of the lower levels in the hierarchies must be factors of topmost level, which is why you do not see an 8-week level in the THEIF 12-week set. The 2 data transforms we're using are either no data transform or a 4th root variant stabilizing transform. And this latter transform was chosen based on some work from my colleagues at Reich Lab showing that this is a useful transformation when working with COVID-19 data. Now moving on to the metrics we use to evaluate the models. there are 4 total: mean absolute error, weighted interval score, 50% and 95% prediction interval coverage. And each of these metrics shown here is actually an average taken over a particular aggregated group of forecasts rather than looking at a single forecast for a single location. Additionally, just want to sort of explain the latter 2 metrics just a little more. Weighted interval score measures how closely a set of prediction intervals is consistent with the true value we're trying to forecast, and it's made up of 3 components, which are spread, over prediction, and under prediction. And for alpha level prediction interval coverage, we are not looking for 100% coverage. We are looking for alpha percent coverage. Lastly, we are also using relative versions of mean absolute error and weighted interval score in our analysis in order to do some adjustments for forecast difficulty level, because not all forecasts are equally easy or difficult to make. So for example, relative WIS is WIS of model M divided by the WIS of the baseline for a particular forecast. And through this definition, we can see that the baseline will always have a relative WIS of 1. So now this brings us to the results. First, I want to direct your attention over to figure A, which shows 1 to 28 day ahead instant hospitalizations forecast for the US national level. Shown here are a top performing model, a poor performing model, and the naive baseline I mentioned earlier. Something I want to draw your attention to is the fact that the 2 thief models have narrower prediction intervals than the baseline model does, and they are actually predicting the direction of the trend compared to the baseline, which is flat throughout its forecast. Now onto the tables. Table B shows the overall metrics for the US national level forecast, models ordered from lowest WIS to highest, where we're trying to achieve the lowest WIS. Table C is the overall metrics average over the 50 states, DC, and Puerto Rico. The reason for this split is because there's sort of a very big difference in scale for numbers of hospitalizations between the 2, and so we don't want to have the results muddled by combining them into one. So to sort of summarize what's going on in these tables, we're not really seeing the models overall beating the baseline for most of these metrics. The 2 best models, the thief 4-week 4 root and thief 8-week 4 root, basically are just sort of getting close to the baseline's performance. But the place that we do see improvement is in the 50% coverage. And you can see that we are getting much closer to the nominal level 0.5 with the thief models, which is explained by the fact that they have much narrower prediction intervals. And then lastly, just to note that the model ranking order between the 2 tables is very similar. Now we consider a breakdown of the results by horizon week. We only show the average WIS by horizon week graphs here, not any of the mean absolute error ones, just because they are very similar to the WIS graphs. So we see some sort of similar trends between the US and states level in terms of the shapes, even though the scale is obviously different. And something interesting is that all of the models are performing worse relative to the baseline for the 1 week ahead horizon. Likely due to overconfidence and having just prediction intervals that are a little too narrow. And the thief 4-week 4 root model seems to be doing the best in both the US national level and the average states level, which was consistent with what we saw in the previous slide. And then to talk about coverage rates, though they're not shown here, the 50% coverage rates for both the states and US national level are much closer to the nominal level compared to the baseline, which is constantly having coverage that is much too wide. Now we do a split by pandemic wave for the results, and we see a sort of overall similar shape in trends for the models, where we've got the weighted interval score increasing as horizons increase. We've got, again, the worst performance compared to the baseline for the 1 week ahead horizon due to overconfidence, mostly during the winter 2021 waves, a little less so for the alpha waves, in which performance is a little bit better or more comparable to the baseline. And then additionally, we have this sort of similar performance between the top 4 models, which is especially pronounced in the alpha wave compared to these 12-week thief models for both the US and the states level. But something that's interesting about those 12-week models is that they have significantly better performance that approaches or even beats the baseline for some of the longer horizons during the winter 2021 wave, most pronounced for the US level, but also true to some degree for the states level. And then to talk about coverage again briefly, we often saw some poor coverage for the US level, especially for the 1 week ahead and during the winter 2021 wave, but coverage is a little better for both waves at the state level. And then we get to our final breakdown, which is by location. And this figure to the right shows the overall relative risk stratified by location, which is aggregated across all horizons for the entire training period. The x-axis has the models ordered by overall relative risk, while the y-axis has locations ordered by descending cumulative hospitalizations. And so here we get a sort of similar ordering of model performance that we saw in the other breakdowns. And another thing is that the models generally perform worse with these higher count locations, as sort of evident by the greater amount of red shown in the top of the figure. And we've actually seen that in other work that higher count locations are actually harder to predict. So our results are consistent with that prior knowledge. In terms of conclusions, we can say that the top 2 best models are the thief 4-week forward, as well as the 8-week forward. The 4-week version has performance pretty comparable to the baseline for most metrics at both the US and the average states level, while the 8-week forward is maybe a little worse than the baseline, sort of second best overall. Also, the 4-week no transformation thief model was a close contender for that second place. We also have a category best of the last 12 weeks, which was included just in case any of the models seem to perform better with more data to train on. And that goes to thief 8-week no transformation, and it beat out the other candidates based on having better coverage rates and an overall performance comparable to the baseline for those last 12 weeks. And then third, the 12-week horizons don't seem to be super useful for our short-term forecasting, which is 1 to 28 days ahead, except in the case of times of changing trends and high incidence shown by the pandemic wave breakdown. So that's kind of an interesting takeaway. But our overall conclusions is that thief's greatest strengths compared to the baseline are its narrower prediction intervals and its ability to predict trend direction. So in terms of future work for this, we're hoping to add a couple more models to the evaluation, including ARIMA and SARIMA 7 models, which are non-hierarchical for a comparison against the thief models. And this is just to see if it's the thief approach that's giving us these results, or if just the ARIMA-based forecaster is sufficient to see similar things. Additionally, we want to look at more thief models that have shorter top-level aggregation levels, since we saw that it's the 4-week and 8-week thief models as is that seem to do the best in this initial analysis. And then, of course, we want to perform the testing phase analysis on the best models and to see how they do against other models in addition to the baseline. All right, and so that brings me to the end of the presentation. Thank you for listening, and I will open the floor for questions.
Thank you, Lee. Nice talk. Do we have any questions? Please feel free to unmute yourself or put something in the chat. So I'll try to ask a question here because I'm not sure if I understood the model completely, but
Sure.
I mean, this question of the coherence, do you see times when there is a lack of coherence or that the models don't aggregate correctly? Or is that built into the thief model?
It's built into the thief
Okay.
model so that there's
Okay.
not an issue, but there are like other instances of different types of models that could have that issue.
I see. Got it. Okay. That part, I guess, just sort of missed me.
Yeah, just to explain a little more, it's the final step in the creation of the thief models that's like make them coherent, because they actually do not start off necessarily as coherent.
Got it. Okay. Got it. Thank you. Other questions, comments, as I try to wrap my head around this model that I'm completely unfamiliar with?
If anyone's interested, actually, I can link back the original paper about thief that kind of goes a little bit more into it. I sort of gave a very brief overview of the methodology, but I could prepare that link if people are interested.
Sure, that'd be great. Thank you. Other comments for Lee? All right. Okay, well, then maybe I'll say just thank you, Lee. Nice talk.